Welcome to Lesson 19, L'Hopital's Rule and Indeterminate Forms. So you might remember way back in, let's see, was it lesson 4? When we first learned about limits, we talked about 0 over 0 being an indeterminate form. It means that we cannot tell anything about the limit. We can't say if it exists. We can't say it doesn't exist. It literally does not tell us anything. So in this lesson, we are going to learn about more of these indeterminate forms that don't tell us anything about whether a limit exists or not. And then we're going to learn about a rule that was devised by a French mathematician that we can use to help us find the limits in these situations with indeterminate forms. So that is what we are doing here. And it's kind of the last bit that we need. It seems a little bit like, wait, we're doing all this stuff with graphs and now we're doing limits again. But that's because if you try to take a limit at infinity, like to determine end behavior, you often end up with one of these indeterminate forms. So this is kind of like the background for how you can then find those limits to complete your work on graphing. So let's take a look first at what the indeterminate forms are that we're going to be dealing with. So we are familiar with the 0 over 0. Similar to that is infinity divided by infinity. It isn't necessarily 1 or 0 or infinity. We just don't know. Then we also have the product of 0 and infinity. We can't say what that's going to give us. And then I think we've talked about infinity minus infinity in the notes somewhere before. Infinity plus infinity is just infinity. But if you're subtracting two things that both go to infinity, how do you know which one's going to win? So that's an indeterminate form. And then we have three different exponential indeterminate forms: 0 to the 0, infinity to the 0, and 1 to the infinity. All of these, if you are taking a limit and you do some kind of direct substitution and you get this one of these forms, then you have to stop and try to get it out of that form in some way. And so L'Hopital's rule is one of the most effective ways to do it. We didn't learn it back in lesson 4 because you need to be able to do derivatives in order to do L'Hopital's rule. So the rule tells us that if we have two functions that are differentiable and the limit of f as x approaches a is 0 and the limit of g as x approaches a is also 0, then the limit as x approaches a of f over g, so if we had just subbed in, we would have had 0 over 0, is actually equal to the limit as x approaches a of f prime over g prime. So let's kind of break that down so we're sure that we understand what it's saying. Okay. So this rule says that if direct sub results in 0 over 0, which is what this step right here is basically telling us because these two limits are both 0, then what you can do is you can differentiate the top or the numerator, differentiate the top and bottom separately. So you'll notice separately, I don't know how to spell that word. You'll figure it out. You'll notice that if you look at this, it's just f prime over g prime. We're not doing a quotient rule. It's no low-d high. It's not the derivatives of the whole things. It's just derivative of the top over the derivative of the bottom. So I just want to make sure that that's clear. This is not using the quotient rule. Okay. And then try direct sub again. So when does L'Hopital's rule apply? It's when you're finding a limit. Okay, it's not that you're trying to take a derivative. It's that you're finding a limit. You end up with 0 over 0. Then you can just take the derivative of the top and the derivative of the bottom and try again. And this little note here in the yellow arrow just tells us that we could have replaced this x approaches a with from the left or from the right, or approaches infinity or approaches negative infinity, all of the possible limits that we have already learned. So let's go ahead and try to apply this rule in some examples. So we're going to start with the limit as x approaches 1 of ln x over x minus 1. So what's the first thing we always try anytime we have a limit is direct sub. So ln of 1 would give me 0, and 1 minus 1 would also give me 0. So this is a 0 over 0 scenario. So we're going to go ahead and try to apply L'Hopital, which is something we couldn't do before because we didn't know what derivatives were. So the derivative of the top over the derivative of the bottom. So you'll notice that's just the limit as x approaches 1 of 1 over x. And if we try direct sub again, we get 1 over 1, which is 1. So here's a great example where 0 over 0 gave us an actual limit that equals 1. Okay, trying again. Let's see, as x approaches infinity. Well, as x approaches infinity, the top would be like 1 over infinity because of the negative exponent, which is 0, which goes to 0. And this would be sine of, let's see, 1 over infinity here would also go to 0, and sine of 0 is 0. So once again, we have a 0 over 0 scenario. So these derivatives are going to be a little bit more involved. Let's see, I need to subtract 1 on the exponent, so that would give me negative 7/3. That's a negative, it's kind of small. Then I'm going to need the chain rule, so I'll take the derivative of the sine, and then I will multiply by the derivative of the 1 over x. And I could have written that, if it might make it easier to write that as negative x to the negative 2, because I do see that I have an exponent on the top on an x as well. So if I want to simplify, it might be easier to write it that way. So that's exactly what I'm going to do next, is I'm just going to try to clean this up a little bit before I apply my direct sub. So the negative 4/3 will break down. Actually, you know what? I think I'll just leave that on top for now. And actually, okay, let me try my approach here one more time. So I have a negative over a negative. That's going to give me a positive. I'm going to leave that 4/3 here for the moment. It doesn't really matter. I could have moved the 3 down. And then I'm going to do this top exponent minus the bottom exponent. So negative 7/3 minus 2, so it'd be plus 2. Negative 7/3 plus 2 would be negative 1/3. So I have an x to the negative 1/3 on top, and I have a cosine of 1 over x on the bottom. So let's see if we can apply direct sub again. So if I'm approaching infinity on the top, this is still x to a negative power. So it's this part here is going to go to 0. That would make this whole thing go to 0. And if I apply the infinity on the bottom, 1 over infinity is going to go to 0, and cosine of 0 is 1, not 0. So this comes out to 0 over 1, which is in fact 0. So like I said, I could have simplified like this, and then I would have had a 3 on the bottom instead of a 1, but it wouldn't have mattered because 0 divided by 3 is still 0. All right, so why don't you go ahead and pause the video and try number 3. All right, let's take a look. When we plug in 0, I get 0 minus 0 over 0. So there we are. I'll take my derivative of the numerator. I get 1 minus cosine x, derivative of the denominator, 3x squared. Plug in again, I have 1 minus 1 and 0. So I have 0 over 0 again. So I'm just going to apply L'Hopital again. I'm going to take the derivative of this over the derivative of this one more time. And yet again, I get 0 over 0. So I'm going to try it one more time. And in that case, I now have 1 over 6. So the kind of the rule or the lesson learned from this example is you're able to apply L'Hopital's rule multiple times in one problem till you can get down to something that's not indeterminate. Okay, and then you can also apply the same exact rule to situations where you get infinity over infinity. So 0 over 0 and infinity over infinity are basically treated the same way in L'Hopital land. You're still going to take the derivative of the top, derivative of the bottom, and try again. So let's take a look at one of these. I have the limit as x approaches infinity. Ln of x will approach infinity slowly, but it gets there. And same with the square root of x. It also slowly approaches infinity. So now I am looking at using L'Hopital. So I have 1 over x on the top as my derivative. And the denominator, again, you could write this in different ways if you want to. That's one way to write it. The 2's are going to cancel. I'm going to clean this up first because I've got a fraction over a fraction. What does that actually give me? So I have the top times the reciprocal of the bottom, which is really, right, square root of x over x, which simplifies down to 1 over the square root of x. So it is really important when you're applying L'Hopital's rule to make sure that you simplify the expression that you're dealing with before you try direct substitution. It's really important in any limit that you do that. So now if x is going to infinity, the bottom is going to infinity, and 1 over infinity will go to 0. All right, go ahead and give number 5 a try. All right, I've got infinity plus 0. E to the negative infinity approaches 0 over infinity. So I take my derivative, and this part is still going to 0. So it's just going to give me 5/7. Okay, just a word of caution. When you start learning L'Hopital's rule, you just want to make sure that you don't start using it in places that you can't. So for example, if the following limit, we have the limit as x approaches pi from the right, doesn't really matter, of sine of x over 1 minus cosine x. So when I do direct sub, I get sine of pi, which is 0. That was kind of a strange looking 0. And then cosine of pi, what is the cosine of pi? It's -1. So I have 0 over 2, which is 0. So there is no L'Hopital to be used here. In other words, this is not an indeterminate form. So you just need to be sure that you always start every limit with direct substitution, and then you double check. Oh, okay, I've got an indeterminate form, and then you can try to apply L'Hopital's rule. All right, there are the one more form we're going to include in this group because it really is just 0 over 0 or infinity over infinity in disguise, which is 0 times infinity. Okay, so when we get these, we're going to convert them to a 0 over 0 or infinity over infinity form. Okay, and the way we do this is we're going to move one of the two functions into the denominator, but we can't just move something to the denominator. So we're going to put its reciprocal in the denominator. So it's like we're flipping it twice, which means we're not really flipping it at all, right? If you put something, a reciprocal in the denominator, it's equal to itself. Let me show you a quick example. So if I take like the number, well, let's just start with x, okay? Its reciprocal is 1 over x. So if I move 1 over x to the denominator, which would just leave 1 in the numerator, that's the same as the numerator times the reciprocal of the denominator, which is just what I started with, right? So we took this, we put its reciprocal in the denominator, and that's still the same thing. So we're going to choose one of the two functions to move its reciprocal to the denominator, and then we will have 0 over 0 or infinity over infinity, and we can apply the rule. Okay. So let's take a couple of examples here. The first one is the limit as x approaches 0 from the right of x, which would give me 0, times ln of x. So as we approach 0 from the right, ln x goes to negative infinity. So this is one of those situations with 0 times infinity, negative infinity counts. So when you go to flip one of these and put them in the denominator, you really just want to think about which one of these, when you take its derivative, its reciprocal is not going to be crazy. So would you rather take the reciprocal of 1 over x or 1 over ln x? I would definitely rather do 1 over x, right? Ln x is going to give me a bigger issue if I have to take its reciprocal and then do the derivative. So we're going to leave ln x on top and we'll move the reciprocal of the x. So that would be 1 over x to the bottom. Double checking, we still have infinity on the top, but now as x goes to 0, 1 over x goes to infinity. So that's the indeterminate form that allows us to use L'Hopital, derivative of the top, the derivative of the bottom, and simplify, back to simplifying. I will have a negative, x to the negative 1 over x to the negative 2 will just be x. And so that is going to go to 0. Okay. If you need to just work this out on the side with a little bit more I already had taken care of the negative, right? You take the numerator, you multiply it by the reciprocal of the denominator. You can see how we get that. All right, so same idea. Give number 2 a try. All right, let's take a look. So if I approach pi over 4 and use direct substitution, tangent of pi over 4 is 1, so that will be 0. And secant, oh, I'm going to multiply the pi over 4 by 2, so that would be pi over 2. The secant of pi over 2 does not exist. It's approaching infinity because the cosine of pi over 2 is 1. So I have 0 times infinity. So I need to pick one of these two things to move to the denominator. And when I move it, I will be taking its reciprocal. Well, again, 1 minus tan x is going to give me a pretty messy chain rule to take a derivative of if I put it in the 1 over that. But 1 over secant is just cosine. So I moved the secant of 2x down to the denominator and flipped it to make it a 1 over secant of 2x, which is the same as cosine of 2x. That gives me a 0 over 0. So then I take the derivative of the top and the derivative of the bottom and direct sub again. And I'll get 1 as my final answer.